Welcome back to the deep dive. Today, we're plunging into a manufacturing process that's, well, it's surprisingly pervasive, yet often kind of invisible in our daily lives. Aluminium extrusion. Now, anyone familiar with advanced manufacturing, you probably know this is more than just, shaping metal. It can be almost an art form. So our mission today, we've got some great sources, and we want to really unpack what makes this process so uniquely powerful for today's complex designs, how it actually works, and why it's such a fundamental building block of modern manufacturing.
Absolutely. And as we get into it, you'll find it's this really remarkable blend of engineering, precision, material science, and even, yeah, design artistry. This process is kind of the unsung hero, enabling countless products we interact with every single day. Think like the frame around your window or even critical components in an airplane.
Okay, so let's just dive right in then. When we talk about extruding aluminium, is it really as simple as, say, squeezing toothpaste out of a tube with a shaped opening? Or is there a lot more nuance involved in getting those incredibly precise shapes?
That's actually a great starting analogy, yeah. It captures the basic idea. You're forcing material through a die. But yes, that simple toothpaste idea hides a whole mountain of engineering complexity. Fundamentally, aluminium extrusion is a manufacturing process that transforms raw aluminium into objects with a really definitive, consistent cross-sectional profile. But what's truly insightful here isn't just that it can be tailored, it's that this lets engineers um, consolidate multiple parts into one single extrusion.
Oh, okay.
Think about that. Instead of making and then assembling, say, 5 separate pieces, you can design and produce a single integrated profile.
Right.
That dramatically simplifies assembly, it reduces weight, and often it performs better than welded or riveted structures. It's an economic and a structural game changer, not just, a design perk.
Wow, okay. So it's not just about the shaping itself, it's about optimizing the whole part right from the beginning. And that incredible design flexibility, combined with aluminium's natural properties, that's what makes these extrusions so valuable. We're talking lightweight durability, fantastic corrosion resistance, and an exceptional strength-to-weight ratio. You might not even realize it, but you find them absolutely everywhere. From the sleek casings on modern electronics to high-performance car parts, even the structural frames of, like, sports equipment, they are totally integral to modern products.
Exactly. It's that versatility that allows for products like, say, a custom LED lighting fixture to have heat sinks and mounting points built right into its profile instead of having to bolt on separate components later. It's really elegant problem solving.
Okay, so here's something I found really interesting. This whole concept of extrusion, it isn't actually new at all, is it?
Not at all.
The origins apparently date all the way back to 1797. That's when the technique was first patented for producing lead pipes. Can you imagine? That must have seemed incredibly cutting edge back then.
It really is a testament to some enduring engineering principles, yeah. But the real leap, as you sort of hinted, came later with hydraulic presses. That was in the 1820s. That's what truly mechanized and scaled the process. It allowed it to move beyond soft metals like lead to tougher materials like copper and brass.
Right.
And then by the late 19th century, aluminium extrusion really found its niche. That's when it started evolving significantly, growing into critical sectors like aerospace and architecture, places that really need that unique mix of strength, lightness, and precision that aluminium offers.
What do you think the biggest hurdle was transitioning from something soft like lead to aluminium, which is much harder?
Well, I guess it must have been the sheer force needed, right? Lead is so malleable, you could probably almost push it by hand, but aluminium needs a lot more persuasion.
Exactly. So how do they manage that today? Walk us through the modern process, because I imagine it's come a long way since those early days.
You're absolutely spot on. It's all about immense controlled force. Let's take a quick journey through the 6 key steps of the modern aluminium extrusion process. It really all begins with what you might call the blueprint, designing the die.
Okay.
And this isn't just any old hole. It's a custom extrusion die, meticulously engineered to the exact profile needed. These dies are constructed from incredibly hard materials, like hardened steel or even tungsten alloy. And that's precisely because they have to withstand just enormous pressures and very high temperatures without deforming even slightly.
Makes sense. So once you have that super tough die, what happens with the actual aluminium?
Right, that's step 2, preparing the aluminium billet. The raw material, which is usually an aluminium billet, basically a solid cylinder of aluminium alloy, is heated up. It goes to an incredibly precise temperature, typically somewhere between 350 and 500 degrees Celsius.
So not melting?
No, not melting it. It just makes it pliable, sort of like a very stiff clay, ready to be molded. Once it hits that perfect malleability, it's cut to an optimal length for the press.
And then comes the main event, the actual shaping.
Exactly. Extrusion itself. This is where that softened, heated billet is pushed through the die using a really powerful extrusion press. Often it's a hydraulic ram applying just immense controlled force. This is the moment the aluminum actually takes its final shape, emerging from the die as a continuous profile with those consistent dimensions and the really smooth finish we often see.
Okay, so it's emerged, it's perfectly shaped, but I imagine it's still incredibly hot. You can't just leave it to cool down on its own, right?
No, absolutely not. If you did, it might warp or lose its shape. So the next critical step is cooling. Rapid cooling is vital here. It locks in that new shape, it retains the structural integrity, and it prevents any warping or, unintended deformation.
How do they do that? Just fans?
Well, depends. The method varies based on the complexity and the thickness of the profile. Simpler shapes might just be air-cooled on a cooling table, but more complex or intricate profiles might need a water spray or even full immersion in a water bath for really rapid solidification and precise control over the cooling rate.
Okay, so it's cooled, it's solid, it's stable. Is that pretty much the finished product then?
Almost, but not quite. After cooling, it moves on to finishing. The long extrusion, which can be, tens of meters long, is first cut to the desired final length, and then very often it undergoes surface treatments. We're talking options like anodizing.
Right, I've heard of that.
Yeah, it electrochemically creates a really hard protective layer on the surface.
Yeah.
Or powder coating, where the dry powder paint is electrostatically applied and then baked on for extreme durability and color. And these treatments aren't just cosmetic, they significantly enhance both the durability, corrosion resistance, and the overall functionality of the part.
Gotcha. And then presumably one last check before it goes out the door.
It's exactly. The final safeguard, quality control. This is a really meticulous final inspection. The finished profiles are checked for dimensional accuracy. Are they exactly the right size and shape? Surface quality, any blemishes. And mechanical strength, does it meet the required specs? It's an absolutely essential step to ensure every single piece meets the exact specifications and, frankly, the demanding standards required by industries like aerospace or construction. What's truly impressive here is how each step, really from the die design right through to this final inspection, is so carefully controlled. It ensures the final product meets exact specs. It's a real testament to modern precision engineering.
And to make all of that happen, you obviously need some pretty serious machinery. Could you just briefly highlight the main components we'd find in an aluminum extrusion line?
Sure. Yeah, it's quite a setup. At the very beginning, you've got the billet preheater. Does exactly what it sounds like, heats those billets to the precise temperature needed for optimal flow. Then there's the heart of the operation, the extrusion press itself. Usually a massive hydraulic press that applies that immense force we talked about, pushing the billet through the die.
Right.
After the extrusion emerges, you have the cooling systems, whether air, water spray, or immersion tanks. Absolutely essential for shape retention and preventing warp. And finally, you typically have a puller and cutoff saw. Automated pullers gently guide the extrusion as it comes out, keeping it straight, and then computer-controlled saws precisely cut it to the exact length needed. It's a beautifully synchronized, often automated process.
Now, you might think, okay, extrusion is extrusion, but what's fascinating is that there isn't just one way to do it. Different methods suit different needs, right? What are the main types we should know about?
That's true. The ingenuity extends to the methods themselves. One really common one is direct extrusion.
Okay.
In this process, the billet is loaded, and a ram pushes it directly through a stationary die. It's pretty straightforward. Ideal for simpler profiles like solid rods, bars, basic tubes, that kind of thing.
And then there's a method that sounds, well, almost the opposite, indirect.
That's right, indirect extrusion. It's a bit more complex. Here, the die is actually mounted on the ram and is pressed against the stationary billet, forcing the metal to slow back through the die.
Huh. Why do that?
Well, the main advantage is that it significantly reduces friction between the billet and the container walls. This means you need less pressure, and it allows for more complex shapes to be created. The result? Extrusions often have even better dimensional tolerances and uniformity, crucial for high-precision applications.
Interesting. And what about for very specific things, maybe smaller products or thin walls?
For that, you often see impact extrusion. This technique uses a high-speed, high-force impact, like a punch hitting a slug of aluminum in a die cavity. It's used to produce hollow or very thin-walled profiles. Think things like aerosol cans, battery casings, collapsible tubes. It's all about achieving extreme precision and thinness for specific container or sometimes structural needs. These different types really highlight the incredible design flexibility that aluminum extrusion offers across just a huge variety of industries. They're solving very specific engineering challenges.
So if we step back now and kind of connect all these pieces, what does this all mean for us? Why is this process such a critical enabler, such a cornerstone of modern manufacturing? Beyond the obvious shaping, what makes it so indispensable?
Well, there are several really powerful advantages, and some of them are truly game-changing, I think. First, that design flexibility we keep touching on. It's not just that aluminum extrusions can be tailored into intricate profiles, it's that this capability allows engineers to innovate solutions that were previously just impossible, or maybe way too cost-prohibitive with other methods. It really empowers complex, multifunctional designs.
And the material properties themselves are obviously a huge part of the equation, too.
Absolutely. The lightweight and durable nature of aluminum is just vital. Its exceptional strength-to-weight ratio means you get durability without adding unnecessary mass. And that's non-negotiable for industries like transportation, aerospace, even electric vehicles now, where every single gram counts towards efficiency and performance.
Right. And thinking from a manufacturing standpoint, what about the bottom line? Is it expensive?
That leads to another key point, cost efficiency. The extrusion process itself, especially the tooling the dies, can often be relatively inexpensive compared to, say, setting up for casting or machining complex parts from a solid block. This significantly reduces setup costs and often production time, too, making it incredibly competitive for both small, custom batches and large-scale mass production.
And maybe most importantly in today's world, what about its environmental footprint?
This is where aluminum truly shines. Sustainability. It's one thing to say aluminum is recyclable, right? Lots of things are. But the real insight here is that aluminum is infinitely recyclable without losing its inherent material properties.
Infinitely.
Pretty much, yeah. An aluminum window frame from, say, 50 years ago can literally be melted down and become part of a brand new car chassis tomorrow with almost no degradation in quality. That's a true circular economy in action. It really sets it apart from many other materials and makes it a hugely responsible choice for manufacturing.
That's incredible. And finally, you mentioned finishes earlier, the aesthetic possibilities.
Yes, exactly. The versatile surface finishes. You have that huge range of options like anodizing for durability and color, powder coating for even more colors and toughness, painting, even mechanical finishes like brushing or polishing. These enhance both the appearance and the functionality, protecting the material and allowing designers to make it fit seamlessly into almost any design aesthetic. So when you really consider all these advantages together, the precision, the lightweight, the strength, the cost, the sustainability, the finishes, it becomes really clear why aluminum extrusion is such a fundamental backbone of modern manufacturing. Its ability to produce these high-strength, lightweight, incredibly precise, and complex profiles just continues to drive its adoption across more and more diverse sectors. For you listening out there, what truly stands out as a game changer among these advantages?
That's a good question. For me, I think it's that powerful combination of the design flexibility, allowing for that part consolidation and intricate shapes, coupled with that infinite recyclability. It feels like a process that enables incredible innovation while simultaneously being incredibly responsible from an environmental standpoint. It really is a powerhouse, crafting so many complex, durable, and eco-conscious components that make up our modern world.
It really is. So maybe a final thought for everyone listening. Next time you look around you, maybe at home, in your car, or even at the office, try to consciously consider how many everyday objects might owe their existence, or at least their performance and efficiency, to this precise, often hidden process. Look for those distinctive profiles, the clean lines, the integrated features. You might see extruded aluminum in window frames, heat sinks, railings, car trim, maybe even parts of your phone or laptop. Take a moment to appreciate the ingenuity behind them.